So it's an extraordinary pleasure to introduce Professor Claire White. Claire's work truly exemplifies the beauty of material science. So her work focuses on optimizing engineering and environmental materials. These include sustainable construction and carbon capture. And as a result, her work not only expands the frontiers of material science knowledge, but it also addresses existential environmental challenges. I'll just tell you that Claire is a superstar. She's an associate professor in Princeton's Department of Civil and Environmental Engineering, and she's the acting associate director of the Andlinger Center for Energy and the Environment. She holds associate faculty status in multiple departments across Princeton. These include departments of chemical and biological engineering. She's also holds an associate faculty status in the Department of Mechanical and Aerospace Engineering. It really highlights Claire's broad base of expertise. She also holds faculty status in the Princeton Institute for the Science and Technology of Materials, High Meadows Environmental Institute, and Princeton Institute for Computational Science and Engineering. She's a recipient of numerous awards. This includes the NSF Career, the Gustavo Colinetti Medal, and Howard B. Wentz Junior Faculty Award at Princeton. And not only is she exceptional in her research and has been recognized for that, but she's also an exceptional teacher. She's been recognized many times for outstanding teaching as a member of the faculty at Princeton University. So let's give Claire a warm welcome, and looking forward to hearing about the material science of sustainable cements. Take it away, Claire.
Sounds good. Thank you very much for that kind and overly embellished introduction. I'm always well, it's great to hear when people talk like this, but it always makes me feel a little bit embarrassed. Nevertheless, I'll get started. So before I begin, what I want to let people know is I have the chat window open on Zoom. So if there's any questions as I go along, do feel free to type them in the chat for those of you that are virtually attending. If you're in the audience there, I don't know how easy it is to kind of shout out and ask a question, but I'd prefer if you have a question to ask it as opposed to wait to the end. So we'll see how we go. So as Ryan mentioned, I have a joint appointment between Civil and Environmental Engineering and the Andlinger Center for Energy and the Environment. But I also am associated with essentially the Materials Center. We don't have a materials department on campus, we have a center. And so what this means is, although you can't, because we don't have the department, it's a little bit different, but there's a lot of faculty on campus that do materials research, and so it's based around this center. So introduction to the research and what sorry, I've got to get this one to work. What I focus on, the basis or the motivation for the research really stems from, I think it's been a while with Zoom. So here we go, I got it working. The basis for the research stems from sustainability and CO2 emissions. So a lot of people are, well, you're all aware of electricity generation and the fact that fossil fuels, if you burn them, you generate CO2, which is being released into the atmosphere at present. The same is true for if you're heating and cooling buildings. CO2 at the moment is being released into the atmosphere due to the energy requirements. What's not so well known is that there's certain industries that are also contributing to CO2 emissions. And so if you look at the engineering materials that we use, concrete and steel, one component in concrete, it's manufacturing, the cement powder. It's actually responsible for about 8% of all anthropogenic CO2 emissions. And then if you look at steel production, there's two steps to it. And you add those together and look at the emissions associated with those, you're looking at 7% of all anthropogenic CO2 emissions. So these two industries alone account for quite a portion of CO2 emissions that's contributing to climate change. So what can we do about this? Well, if previously with the industries, they would say, well, we can't not build with concrete, we can't not build with steel. We're going to have emissions associated with them. But more recently, over the past couple of decades, there's been an understanding that there are innovations that can happen in these industries, and there are ways that the CO2 reductions can be achieved. And so I'm not going to go into all of the details, especially for iron and steel. I'll mention a couple for concrete. But through the material science research, in conjunction with engineering and applied research, there's inroads being made to how we can make concrete more sustainable, yet have it perform in the same way that current day concrete is performing. So in terms of, in addition to being able to decarbonize the steel industry through, say, using hydrogen fuel instead of fossil fuels, there's also some alternative materials that can be used, such as carbon fiber reinforced polymers. But if we look at concrete itself, what I'm going to explain is where the CO2 emissions come from concrete production. One of the steps involves decomposition of calcium carbonate, limestone, which is abundant on the Earth's crust. And it's hard to avoid the CO2 emissions that's associated with this decomposition process that happens in the kiln. But there are ways that people are they're tackling this challenge, and I'll go into a little bit of detail soon. So to give you a bit of an overview of what my group does at Princeton, we're very much focused on materials and the material science. We look at blended and alternative cements as a means of reducing CO2 emissions associated with concrete usage. But at the same time, we're really trying to optimize these materials, understand them and optimize their performance so that they will stand the test of time when it comes to using them in construction applications. We also do some research on carbon capture materials and carbon storage. I won't have time to talk about that component of the research today, but we have been doing a little bit of investigation of new solid sorbents for carbon capture and understanding both the synthesis of these materials and also how they interact with CO2. So in a nutshell, how I describe the type of research we do is that we use material science approaches to discover and manipulate, so to optimize the fundamental behavior of materials with the idea that we're going to then enhance properties that manifest themselves at the micro and macro scale. And so, for example, we combine atomistic and coarse grain simulations with synchrotron and neutron experiments. And when we talk about cements and trying to understand new types of cements, the kind of information that we're getting at can be very important for understanding larger length scale, like the microstructure and macroscopic properties. So we really concentrate more on the micron length scale and below, with the impact being at the macroscopic length scale. Keep in mind that there are properties that manifest themselves at the macroscopic level in materials where the processes are occurring above the length scale we are looking at. So not all of the behavior of materials, if you look at the macroscopic level, are always tied back into the submicron length scale. But what I'll be talking about today is on the properties that are linked back to the smaller length scales. And so to give you a bit of an idea of what my group gets up to, this is a very common plot that a lot of people show going across time scales and length scales, but we use a variety of both computational and experimental techniques, such as density functional theory, coarse-grained Monte Carlo simulations. On the experimental side, synchrotron and neutron techniques, such as computed tomography, paired distribution function analysis, quasi-elastic neutron scattering. We're trying to get at both the structure of a material, such as like the atomic structure, but we also trying to get at things such as porous materials and what is the pore structure of a material. So Returning back to cement manufacturing, why are there CO2 emissions associated with the manufacturing of cement powder? Well, if you look at the industry, what happens is you dig raw materials out of the ground. Limestone is one, which is calcium carbonate, and also clays. And you heat them up in the kiln to really high temperatures, 1,450 degrees Celsius thereabouts. And so what happens at about 900 degrees Celsius is you get this decomposition of the limestone. And so it forms lime, calcium oxide, and then there's this CO2. The reason why we go to higher temperatures is for the formation of calcium silicate phases that are reactive with water. So we have to go to these really high temperatures to get the right phase composition in the cement powder for it to be able to react with water. And so if you look at the fuels that are used to get to these really high temperatures, such as petroleum coke, the burning of those contribute about 45% of the CO2 emissions. And then this decomposition of the limestone contributes about 55% of the emissions, such that if you look at 1 ton of the cement powder that's produced out of the plant, you're getting about a ton of CO2. So this is not insignificant in terms of the CO2 that's been generated. Now, the industry and the wider community are very much aware of these CO2 emissions. And so there's been a lot done in terms of outlining the various approaches to reducing the CO2 emissions associated with this industry. And it's not just one approach that's needed. There's a variety of approaches that together are needed to reduce the emissions. And so, for example, here, energy efficiency of the kiln, advanced fuels, so not burning coke, petroleum coke. There's this thing called clinker substitution, which is actually the cement powder. If you replace it with some other stuff, you can reduce CO2 emissions, but still get good performance of the concrete. And I'll talk a little bit about that from a material science perspective. And then carbon capture and storage is talked about as necessary in this industry to reduce emissions. There's also down here, I put innovative disruptive technologies and specifically alternative cementitious materials. Essentially, can we make concrete without having to use Portland cement powder? And the answer to that question is yes. And I'm going to talk about today how some of the fundamental research we do on both Portland cement and the alternative cementitious materials is giving us insight into how, are they going to perform well long-term, and how the chemistry of the starting cement could impact that long-term performance. So in terms of what my research group does, we look at this clinker substitution and also the alternative cementitious materials. And beyond the cement industry, we look in general at carbon capture and storage. So before I can show the research that we've been doing, I need to introduce some terminology because some of the phases that we look at have a complex terminology to them. So we have to go through it now. So what happens when you make concrete? Well, you mix Portland cement powder with water, and I say potable water because you can't use briny salt water. And then we mix it with sand and other aggregates, larger aggregates, and then you get concrete. Now, there's many phases that exist in this cement powder. There's actually 4 main phases that then when you react it with water, you're creating 4 more phases. And it's quite a complex system in terms of what's going on at what time. However, it is known that the main phase that gives concrete strength is called calcium-silicate-hydrate gel. And so this calcium-silicate-hydrate gel, people have looked into quite a lot in over decades and decades. And so we have quite a good understanding of CSH gel. And this is cement notation because we have so many elements. The cement community creates, it's got a cement notation. This is not carbon, sulfur, hydrogen. This is calcium silicate hydrate. What's happening now, as we're trying to reduce the amount of Portland cement powder we need to make a certain amount of concrete, is we're adding in other materials. And so, for example, if you add in a glass, or, well, a good example actually is calcined clays, and specifically calcined kalinitic clays. There's a lot of aluminium that comes along. And so what happens is the composition of the gel changes, and so does the structure of the gel. So we have somewhat of a good understanding of this cash gel, but not as much as the CSH gel. And so if we continue going on with other elements, sodium, for example, you can get this CNash gel. Well, sorry, the CSH gel with sodium in it. And then also when you have sodium and aluminium, you get this Canash gel. So we really need to understand what impact the additional elements have on the structure of this gel, and also how, if the thermodynamics of the gel changes. And it's very hard to analyze this gel within the concrete system because of all of those other phases that exist. So what I'm going to show today is some computational chemistry research we've done on just the gel itself, to give us some information on the thermodynamics, and also some experimental results that were found on these, well, that we've discovered for these systems. One thing I should mention right now is I've been saying gel, and a lot of people think gel is like a gooey kind of material that's you put in your hair, for example, or sol gel synthesis for another example. But however, here I'm talking about a mechanically hard material. So it's got high compressive strength. The reason why it's called a gel is because it's not perfectly crystalline. It contains water in it. People have made analogies with sol gel synthesis, and so that's why the term gel is used a lot in the community. Also, we work on alkali-activated concrete. And so this type of alternative concrete you can make using metallurgical slag, so actually amorphous glasses that are in these metallurgical slags. You can use fly ash, which is a byproduct from the coal industry, calcined clays I've mentioned before. But say if you add calcined clays to water, they're not going to react. So we need to activate the clay to get it to dissolve, and then for a mechanically strong binder phase to form, to give concrete strength. And so we use an alkaline activation process, for example, sodium silicate, a high pH system. And then this is alkali-activated concrete down here that's actually been made with a combination of blast furnace slag and also fly ash. And it behaves at the macroscopic level in a very similar fashion to Portland cement concrete, but the fundamental phases within this material are different. And so we want to understand how those phases impact long-term performance of this material. So in terms of the gels that give the concrete strength here, there's once again this Canash gel that exists, but that's only when you have a lot of calcium in your system. If you don't have calcium in your system, say if you've got alkali-activated calcined clays, which are actually low in calcium, you end up with a different gel, which we call Nash. And so the question is, what impact does the different gels have on the performance of these concretes? I'm not going to go into the Nash system today. We're going to concentrate on the calcium-rich systems, but it is very important to understand these differences. Are there certain applications where you want to use one concrete over another, for example? Okay, so what we know and what we don't know. The long-term performance of blended Portland cements and alkali-activated materials is not well established. So this in some ways is inhibiting their use by industry. We need to develop standards and codes that allow for their use, but we also want to be able to predict long-term performance of these new materials without waiting 50 years. And so there is the need to be able to do, the need for fundamental research to help with the prediction of how these materials will perform. And the long-term performance is linked to it's the durability of the material, how resistant it is to degradation. And this can be caused by instabilities in the gel itself. So understanding kinetics and thermodynamics is important. And also the pore structure of this material is very important because there are aggressive chemicals that get into concrete and degrade it. And it's kind of funny to know, well, not everyone knows this, but carbon dioxide actually degrades concrete. There's other ions as well. Well, there's ions as well that degrade concrete, such as chloride and sulfates. And what they do is they permeate through the pore structure of the concrete. And then they can cause phases to dissolve, or they can cause rusting of the steel, and as another example. So the pore structure of concrete is very important. What I'm going to show today is very much at the atomic length scale, but I want to get across it's very important to get across the fact that these systems are heterogeneous, and they're heterogeneous across length scales. The results that we get from the atomistic level can be used to infer what's happening at the macroscopic level, or say how you change the chemical composition, how that might affect macroscopic level. But there are other properties at different length scales, such as the micron length scale, that are also important to know. And so this is X-ray fluorescence data of alkali-activated slag. And you can see here, well, we've circled here unreacted slag particle. There's also these iron-rich particles that are there. The gel's forming, but the gel isn't uniform. There's different compositions. And this is only 8 microns in size. So there's a lot of heterogeneities even at the micron length scale. If you go to a larger length scale, it gets even more complicated. You've got phases reacting, the different particles that you start off with, things forming in terms of the gel, and then concrete itself has aggregates in it, and so that's even at a higher length scale. However, we're going back to the atomic length scale for this presentation, and so our next slide is actually research, but I just want to make sure that we're on the same page with understanding what these gels are. Okay, so on the left on this slide is a representation of the calcium-silicate-hydrate gel without showing oxygen atoms, without showing hydrogen atoms, but just showing the calcium ions and these silicate chains. And so what's known is it has this layered structure at the nanoscale. These chains are of finite length that can be quantified using nuclear magnetic resonance. And then there's these calcium oxide layer, and these calciums is actually interlayer calciums, and they're solvated by water molecules. So this is CSH, and it's quite well known, the structure of CSH. If we add sodium and aluminium into these systems, we know some things. We know that aluminium substitutes for silicon atoms in what's known as these bridging sites, which, for example, is shown here. It bridges across the interlayer region, the hydrated region. And we know that the system has structural similarities to CSH gel. We know that there's these silicate, aluminosilicate chains that exist. They have finite length. The stuff that we don't know so well is what sodium does to the system. And so that's what I'm going to concentrate on today, is can we understand the impact of sodium on the structure of the gel? And can we understand the impact of sodium on the thermodynamics of the gel as well? So the first question we have is about this thermodynamics, and specifically, what is the impact of sodium on the stability of the CSH gel? Is it as thermodynamically stable as the conventional CSH gel? Because this can give us some indication of if the gel is going to change over time once the concrete has been poured in place. And we don't want the gel to change over time, because that can end up causing volume changes for the concrete. It can cause a loss of gel and therefore a loss of strength. It could cause the gel to be more prone to degrade when aggressive ions come in. So we really want to have an understanding of the stability of this gel. So the impact of high sodium concentrations is not well known. And so what we've done here is use density functional theory, computational chemistry, to determine the impact of sodium on some model phases. And so as you're probably aware, with computational chemistry, there's a limitation to what size systems you can study. Larger system sizes, you tend to use force field based techniques. Here we're using density functional theory because we want to get accurate information on the energetics of the system. But we have to compromise on the system size. And so that's why we're using crystalline analogs for what this disordered gel, the gel that we know is not a crystalline phase. So specifically here, we're using what's known as 14 angstrom tobamorite. And we've also used another one known as Clinotobumorite. And so for 14 angstrom tobamorite, the structure is very similar to CSH gel, but these silicate chains are infinite in length. They're not chopped up like they are in the CSH gel. So that's the main difference between the two. So what we did in this study was we substituted the calcium atom in the interlayer with different atoms. And also we looked at the change in the thermodynamics of the system when we put aluminium in on one of those bridging sites for the silicon. We also assessed other potential substitution sites, especially for the sodium and potassium, but they were found to be very unfavorable. These calculations were done using plane wave calculations, specifically VASP, and also the Siesta software. And from these calculations, we can get a variety of properties of the crystal, such as what's the substitution energy cost when you replace, say, a calcium for a sodium? Does that change the overall volume of the system? Does it change bond strength? Can the cations diffuse around more easily? And there's other properties as well. So here's a plot, and I'm going to talk you through the results. What we did was, for every single structure, we calculated what's known as this cohesive energy, which is the average energy per atom that the system gains by the atoms wanting to bond with each other, as opposed to all of the atoms being separate. So this cohesive energy is a way of knowing how strongly the atoms want to bond together in this system. If the atoms didn't want to bond together, then you would have the energy being zero. The other thing that we did here is we calculated the cohesive energy for all of the different structures we had. And then we looked at differences in the cohesive energies between different structures to get a sense of the impact of that substitution on the stability of the material, the phase. And specifically, if you do the substitution, do you have a decrease in this formation energy? If so, that means that there's an energy penalty to having that different atom in your structure. And overall, that means that your structure is less stable. It could be more prone to change over time. And so what you see on this slide here is if you replace a calcium for a magnesium in the interlayer, it is less stable. If you replace the same calcium with sodium, it's even less stable compared to the magnesium. Likewise, if you do a sodium substitution and also an aluminium for a silicon site, it ends up down here. And then potassium's over here as well. I'm not going to go into the volume for the time being. So overall, these calculations show on this slide that any of these substitutions that you do makes a structure that is less favorable from a thermodynamic viewpoint, so not good. However, something that we saw, actually, I'll skip this slide in the interest of time. Something that we saw was if we bring a hydrogen atom into the system as well, along with the sodium, this leads to a more stable structure compared to just, say, the sodium by itself. And so there's a sequence of events that we saw happening when we placed hydrogen into the system near the sodium. And specifically what happened is this hydrogen formed a hydroxyl with the silicate unit close to the sodium. And this also, what we found is that we wanted, it wanted a symmetric charge distribution around the sodium. So we actually ended up with these two hydroxyl units forming, and then there's another hydroxyl floating around in the system. But this ended up with a more symmetric charge distribution around the sodium, which we think is leading to a more stable system overall. So if we do that for the structures that we looked at previously, it does have a very significant impact on the overall energy of the system. And so if we look at the energies of the structures with respect to the original structure, you can see now that if we've essentially charge compensated with the sodium, we're almost as stable as the CSH gel. Likewise, with the sodium and the aluminium, we move even further up on this diagram. So having these hydroxyl units in the vicinity of the sodium and in the vicinity of the aluminium is important in these calculations from a thermodynamic viewpoint. So it's an indication that it could also be important in the real system itself. There's a question that's popped up on the chat, and the question is, are these gels the clinker? They are not. So to describe what clinker is, because I assume that not everyone knows what clinker is, if we go back to this slide here, what comes out of the kiln is actually called clinker. And then that gets blended with gypsum to make Portland cement powder. And then you mix Portland cement powder with water, and that's when the CSH gel forms. So this CSH gel is what's known as a hydration product when you mix the cement powder with water. So just to recap, what we found is essentially a charge balancing mechanism whereby if you replace a calcium atom with a sodium atom, if we have a hydrogen atom that's in the vicinity as well, that's added, then we end up with a stable structure that's comparable to the initial tobumorite crystal structure. Now, you might say, okay, why a hydrogen? Why not another atom? And we also tried one calcium for two sodiums. That's not as energetically favorable. So we found that the hydrogen atom, probably because of its size, is favorable to have, whereas if you're looking at, say, two sodium, they take up too much room, and that's causing some of the issues when it comes to the overall energy of the system. So we can look at things such as bond strength, the impact of having the hydrogen in the system on the bond strength. And so if you look here, this is the baseline CSH. What we're looking at is electron density contour plots between different atoms. And specifically here, we're looking at between an interlayer calcium and surrounding oxygen atoms. If that calcium is replaced by sodium, you see that the electron density contour plots, there's less of them well, the contours, there's less of them. And also they're not as black which is giving you an indication that there's weaker bonding happening between these atoms. However, when there's a hydrogen in the system as well, you can see that the bonding strength has increased. So this is one of the ways that we've been able to get a sense of what hydrogen is having, what impact it's having on the system through this charge balancing mechanism. We also saw what happened in this system without the hydrogen. If you've got a sodium in the system and you've also got aluminium in the bridging site, you don't have a symmetric charge distribution around the sodium. However, when you have charge balance this structure, we do end up with a nice symmetric charge distribution around the sodium, which seems to enhance the stability of the structure. The last thing I'm going to talk about for this part of the research is how easy it is for either calcium or the sodium to move in the interlayer region of the structure, which is that hydrated region. And so we did these calculations whereby we can calculate the barrier to diffusion. Is the atom, can it easily diffuse around, which would be an indication that those elements, well, that element can easily leach out of the system, for example, or is it kind of stuck quite well in its location and it can only diffuse in the local vicinity of where it originally sits. And so here what I'm showing is just for sodium in the interlayer with and without hydrogen charge balancing mechanism. And so without, what we find is the barrier to diffusion is 1.1 electron volts. What you can see is the barrier increases when you charge balance using a hydrogen atom. So this is indicating that you can add sodium to the system. So you can have a sodium containing gel. If you have a sodium containing gel, you can get a gel that probably will perform in a similar manner to CSH gel, so long as you have hydroxylated regions within the material. And what I mean by that is having the hydrogens present that are bonded to oxygens. So you need to have an ample supply of protons for charge balancing to form these hydroxyl units. However, in concrete, I haven't mentioned this yet, but in concrete, the pH is quite high internally. It's about 12.5 or 13. So the higher the pH, the less protons you have. And so this means that you're more unlikely to have this charge balancing that could occur. So what the idea is, could we synthesize concretes using more mild conditions and enhance the stability of these gels? So that's something that we have yet to look at extensively, but is an idea for future research from an experimental viewpoint. Is there ways we can catalyze the gel formation in a concrete system without having such high internal pH conditions? So that's the first thing I wanted to talk about today in terms of research. What we're going to look at now is what happens if we are not just replacing one calcium with a sodium and a proton, but two more calciums in the system. Because the Knash gel that forms, there's going to be different amounts of sodium that's incorporated into the gel depending on how much sodium is in the vicinity when the gel's forming. That's an assumption that we have, is if you have a low amount of sodium when the gel's forming, you only get a little bit of sodium ending up in the structure. Whereas if you have a lot higher concentration of sodium during the formation of the gels, then it's more likely that a lot more sodium is going to end up in the phase, which could affect the performance of the gel. Once again, we did this from a computational viewpoint, and specifically here we used a different structure. I'm not going to go into the details, but it's called Clinotobumorite. There was reasons why we looked at this structure. And so what we did is in the interlayer region, and this is the interlayer region of this structure, we systematically replaced single calcium atoms with sodium, and looked at the energy of the system with replacement, say, of 1, and then 2, and 3, and 4, and so on. Once again, we did these calculations using VAS, and once again, we could analyze various properties of the structures that came out of the calculations. So we can look at the formation energies of these structures with respect to the original Clinotobumorite structure. And so what we can find is that well, I'm going to show it on the next slide when it's with respect to the Clinotobumorite structure, but what's shown on this page is that if you put the sodium atoms in different locations, so you can choose in the interlayer region essentially what substitution to do. That's what we had to do here. We did it manually. What we found is the location of substitution does matter. So if you think about this interlayer region that we have in these gels, there's calcium atoms in that interlayer region. And so do you replace calcium atoms that are in the vicinity of each other, or do you replace calcium atoms as far apart as possible, for example? And so what we found here is we want to have a symmetric distribution of the calcium atoms to end up with a lower energy structure, meaning that it's more stable. Whereas if there's a less symmetric replacement that's done, we found that the structure is less stable. So it's more stable when this the replacement is symmetric. It's less stable when the replacement is less symmetric. What is shown on this slide is that result, and specifically here, this is that energy difference between not symmetric and symmetric for the distribution of the atoms. And what we show here as we go up on the x-axis is with increasing sodium content of the crystal, what happens to the formation energy of the system, which you can think of is there an energy penalty to having sodium in some of the locations where calcium originally was in that interlayer region? And the answer is yes, there is an energy penalty, but it only manifests itself after a certain amount of sodium is incorporated into the structure. And this is interesting. This is giving an indication that you can have some sodium present, but there's a point where you get too much sodium. And so what is likely going to be important from an experimental viewpoint, or from a, if you make these concretes, is you don't want to dose the system with too much sodium, because it could be causing the gel to be less stable, which could make it more prone to change over time. We also looked at some other properties of the structure, such as the bonding strength. And so what we found was that with low sodium contents, you have stronger bonding between the silicon and oxygen. As you go up to really high sodium contents, then you're ending up with a lot weaker bonding between the silicon and oxygen atoms. So this would make it easier for these bonds to break because they're not as strong. So the implications from this these calculations is there appears to be an upper limit of sodium incorporation into this structure, above which the stability of the structure decreases. And so a similar limit to the amount of sodium may exist in the disordered CSH gel structure. And this is still to be proven the case, because what we're doing here is we're using a model crystalline structure to infer what is likely occurring in the disordered gel. But without looking at the disordered gel directly, we can only infer, we can't prove that it's the case. And so, for example, there could be ways of using, say, force field molecular dynamics simulations to explore the same question, but you're looking at also the impact of disorder on the system, so that you're more representative of what we know these gels to be like in real life. So what I should mention, though, there are a bit of caveats from the study that we've done, because there are other differences that we know that occurs when sodium's added to the system in terms of the structure of the gel. So what I showed previously a while ago was I told you that the silicate chains in CSH gel, the conventional gel, they're finite in length. They're a particular length. The length of these chains, when you add sodium into the system, it is known that these chain lengths get shorter. And so this will also impact the thermodynamics of the gel, which we haven't actually looked at with these computational calculations. But on the next slide, we're going to look at this from an experimental viewpoint. So what we've done here is that we've made synthetic gels. So we can synthesize gels that are reminiscent of the real gels in real concrete. And we've synthesized them using different sodium contents and with and without aluminium. Now, there's one thing that people have assumed is that these synthetic gels are representative of the real gels that we find in the real concrete. And I'm going to discuss that today when it comes to one of the alkali-activated concrete, whether this assumption is realistic. So that's one thing we're going to look at. And the other thing that we're going to look at just with the synthetic gels is the impact of sodium on the structure of the gel. So these gels were made with and without sodium and alumina. And what we did was, once we synthesized them, we used nuclear magnetic resonance to look at the silicate connectivity in the gels. And we also used a technique known as X-ray pair distribution function analysis to look at the local structure of the gels. And so firstly, NMR was used to quantify what's known as the degree of silicate polymerization in the gel, where down here is what the silicates can do. So for a silica unit, silicon bonded to 4 other oxygens, that silica unit in these gels could be standalone. It might not be bonded to another silica unit. It might have calciums around it instead, for example. Or it could be bonded to 1 other silica unit. It could be bonded to 2. It could be bonded to 3, or it could be bonded to 4. And so this is known as Q notation, where you go from Q0 up to Q4. Q4 is the most polymerized the silica can be. Q0 is the least polymerized the silica can be. So we can quantify this using nuclear magnetic resonance. And this is what's done on this slide right here. There's the chemical shift on the x-axis. This is silicon NMR. And the spectra give an indication of what Q exists for the silica units. And so here in this region, it's Q0. In this region, it's Q1. In this region, it's Q2. We made a gel using the starting composition of calcium to silicon of 1, and we synthesized the gel in different sodium hydroxide concentrations, no sodium hydroxide, 1 molar, 5 molar. So when you synthesize the gel without sodium hydroxide in there, we end up with this spectrum here, which shows that this structure, this gel, mainly consists of Q2 silicate units. So silicate units tend to be bonded to 2 other silicate units, and that's reminiscent of those silica chains that I was talking about previously. Now, when the sodium content increases, what we find is that things are shifting towards the left on this screen. And so the gel is becoming more depolymerized due to the presence of sodium during synthesis of the gel. So we can actually quantify this change in silica connectivity by actually calculating the center of gravity for each of these spectra. And then I'm going to plot the center of gravity for a whole lot of samples on the next slide. This is what's shown here. So on the x-axis, the gels were synthesized using various concentrations of sodium hydroxide. We actually synthesized gels with varying ratios of calcium to silicon, and we're plotting the center of gravity from the NMR results versus sodium hydroxide concentration that was used for synthesis. And what you can see is this center of gravity decreases for all of the different compositions, which is showing you're going from a high degree of polymerization when there's no sodium to a lower degree of polymerization when there's more sodium. So what this is meaning is you're getting shorter chains of the silicate units when sodium is present, which could make the structure more prone to degradation, which is not a good thing. However, I will talk a little bit about the role of alumina that can combat this, shorter chain lengths. So if you have sodium and alumina, this can lead to similar chain lengths to the normal CSH gel. What we also did was X-ray pair distribution function analysis on the same gels. And so to do this technique, we went to a synchrotron. We specifically went to Argonne National Lab, the Advanced Photon Source. And you can think of it as conventional X-ray diffraction, but on steroids. I don't know if that's a good term. What it is that you're using the high brilliance of the X-rays from the synchrotron to scatter from your sample, which means that you're getting a lot more X-rays being detected, which leads to higher resolution data. It also means that you can, depending on the energy of the X-rays, you can get different 2 theta coverage of your X-ray diffraction pattern, which means that you can do Fourier transforms of your diffraction data and look at the data in real space. And so that's what's shown on this slide to actually get the paired distribution function from diffraction data. This is neutron data, and on the x-axis is momentum transfer. It's related to 2 theta, scattering angle, and y-axis is intensity. And so here we're going out to high Q. This is, if you think about an X-ray, a lab X-ray diffractometer using copper as the wavelength, so a copper X-ray tube, the highest Q max you can get is out to 8. So at synchrotron and neutron facilities, you can get to much higher Q max values. You can cover more of momentum transfer, which means when you Fourier transform the data, you end up with better resolution in real space. And so what's shown over here is a sample that has both diffuse scattering, so scattering from amorphous component in the material, and also these spikes are the Bragg peaks, the crystalline contributions. So you're Fourier transforming both the disordered component, the amorphous or some sort of disordered component if it's present, and also if there's crystalline contributions, you're Fourier transforming that, and you're ending up with your pair distribution function over here, which is a histogram of all atom-atom distances in your material. And so it shows you bond lengths, and then it shows you longer range distances between atoms. And so for something that's predominantly amorphous, which is the case here, a calcium aluminosilicate glass, you've got your bond lengths, and then you end up with some medium range ordering. But once you go out to large distances between atoms, there's no ordering. And so you'll just have the data sitting at around 0. So what we're going to do now is look at the data for those gels that we synthesized using X-ray pair distribution function. And that's what's shown on this slide here. And so what we have is bond lengths. T stands for tetrahedral silicon or tetrahedral aluminium. So there's a silicon oxygen, aluminium oxygen bond length, calcium oxygen bond length. And then we look at distances between atoms. We're no longer in the bond length region. And so what you can see is the different concentrations for synthesis do change the amount of calcium that's in the system, but not so much what's going on out in the medium range ordering. What we did for fun was actually to take the intensity, so the Y value of this data here for this local peak, which is related to the distance between silicon-silicon and silicon-aluminium. And so if you have more of these distances that show up, we think it's a indication of the degree of polymerization of the material. And actually, what we found when we plotted these intensities is, yes, we end up with a similar plot to the NMR data. This is kind of cool. We can actually look at local structure in terms of coordination, whether it's more coordinated or less coordinated with other silicate units, using this X-ray technique. When we compared with the NMR results, which is shown on this plot, there's a trend there. PDF analysis is not going to be, pair distribution function analysis is not going to be as accurate as NMR. But it was interesting to see that we could get this correlation between the two. And so what we find is when you have a high degree of polymerization, we have low alkali concentration, low amount of sodium, whereas if we've got a high amount of sodium, we have a low degree of polymerization. What's shown here in gray is the span for the gels that tend to be in Portland cement concrete. And what's shown here in the purpley blue is the span that we have for the gels that exist in alkali-activated concrete. So it's important with the chemical composition of your system to choose it carefully, because it's nice to be in this region. We're going to have a more polymerized gel. It's likely going to be more stable compared to if we're down this end on the plot. I've essentially said this already, but it's the degree of polymerization that's very important. And so what we found was that as you add sodium to the system, alkalis, it causes the silicate chains to depolymerize. This might be of a concern because the lower coordinated these silicate units are with each other, it's likely easier for the silica to dissolve over time in aggressive environments. But on the flip side, we know that aluminium increases this degree of polymerization, makes it more polymerized. And so that's a good addition to have if you're going to have sodium coming at the same time, which means when you're making concrete, if you're trying to reduce the amount of Portland cement powder and you're using something that has sodium in it, you also want it to have reactive alumina in there as well. Very much lastly, we're going to look at nanoscale ordering of these gels. So I've plotted out to a lot further in R space, in real space, for the pair distribution function. And you can see how the correlations, these atom-atom distances, die off a lot more quickly for this dark sample that's denoted here as AAS compared to the purple sample. There's a difference between these two. One is the gel that's in alkali-activated slag. So it was in a cement sample, and we were able to subtract out other contributions from other phases and look at the contributions just from the gel. And then the purple is just a synthetic gel. There's clear differences in the nanoscale ordering, how ordered the gel is, which can have implications for how people currently use these synthetic gels to understand the Portland cement system. There's a question, yes.
It looks like I might need to ask Miguel to unmute. So just give me 1 minute.
That's the view. You want to click on participants?
Oh. Sorry, just 1 second, Claire. Okay, go ahead, Miguel.
No, I prefer to do it at the end. Okay, I don't want to interrupt, just to finish.
Okay, I'm near the end.
Please.
All right. Well, at least I've got one question. That's great. So the nanoscale ordering is different between the synthetic and real gels, which means that we want to be careful with the results that we get on these synthetic gels to infer details such as thermodynamic stability, but not thermodynamic stability, that's the wrong word, to calculate things such as solubility product of the gel that then gets used in thermodynamic modeling. Because the more crystalline a phase is, typically that means it's more thermodynamically stable, which means that its solubility product is going to be different. So for example, because I know I've kind of twisted this up a bit, let's use an example. Greater crystallinity implies increased thermodynamic stability. And let's use silica as the example here. If you have an amorphous silica versus crystalline quartz, and you look at their solubilities, the amorphous silica is 10 times more soluble compared to the quartz. A similar argument could potentially be the case here, whereby the more disordered gel, this real gel, is less thermodynamically stable compared to the synthetic gel. So we need to be careful about using thermodynamic data, and specifically things like solubility product for the synthetic gels for inputs to thermodynamic modeling, because essentially the community uses a lot of thermodynamic modeling to predict phase composition in the concrete. And the thermodynamic data for the gels comes from these synthetic gels. What we've shown is there's differences in terms of the nanoscale ordering between the synthetic and the real gel in this alkali-activated system. We need to now look at the Portland cement system to see if a similar thing exists between the synthetic and the real gel for Portland cement concrete. There is also potential implications here from an industrial level. There's opportunities to try to increase the degree of nanoscale ordering of the gels in real concrete. If we could do that, then we would be increasing essentially how resistant the gels would be to change over time, especially in aggressive environments. And so this is some of the things that we're looking into is there ways to increase the degree of crystallinity of the gels whilst these systems form? And if so, what impact does that have on their durability, how resistant they are to different aggressive environments? All right. So I'm going to stop. That's it. Essentially, I've talked a lot about sodium in these cement gels and various implications. I'm going to go to the acknowledgement slide in terms of funding, facilities, collaborators, and current students, and I'll be happy to take any questions.
Thank you so much, Claire. Miguel, would you like to start us off?
Yes, thank you. Well, Claire, thank you very much for this really interesting talk. I think I really enjoyed it. And I would like to ask two questions. One is, I am an electron microscopist, and I always, discuss with my friends who do X-ray diffraction that in electron microscopy, we see the radiation damage when we look at the sample, so we cannot get rid of the radiation damage. And many people in X-rays assume that there is no radiation damage. So my question, but there is radiation damage, probably less than electrons, but important. So could be possible that some of the polymerization that you're looking are produced by the X-rays in your experiments? Because the X-rays will increase the polymerization. Do you see that like a possibility that a result of radiation damage? Yeah,
that's a very good question. So we use high energy X-rays around 60 kilo electron volts. There is known for X-rays that you can get significant beam damage for materials in what's known as the water window, which I don't remember the exact values, but it could be around 1 to 2 kilo electron volts. So for carbon and water systems, that's kind of, you're using X-rays in that region. You want to be very careful because you are ending up with beam damage. From the studies that we've done, whereby if we expose the sample to X-rays and we look at changes over time, we haven't seen any indication that, if you have a very short exposure versus longer exposures, that we're getting change in the scattering pattern, which would indicate a change in the structure due to beam damage. So from our results, we don't have an indication that it is occurring. And
I'm sorry,
Yeah, we've also done like time-dependent studies. So we actually follow how these cement forms over time, and they do agree with other experimental techniques such as NMR and others. So we think the beam damage doesn't occur because we're not in the water window where it's known to be significant.
Okay. And then, well, I just want to mention that now in the electron microscope, you can put samples in a liquid stage, okay? And you can use very, very low electron diffraction to do also PDF, which is very, very good. But I have another question, which is very important. What is your opinion of adding to the concrete some materials based on carbon, such as graphene or carbon nanotubes or some, which are totally inert, they do not react? Do you think that will be a benefit, assuming that one can produce these materials cheaply? Do you see any advantage?
Yeah, I'll answer that. I want to go back to the statement about electron diffraction and like pair distribution function analysis. I've always wanted to do that, and I've never gotten around to it. But I mean, we've got questions about the local structure of the materials at like spatially resolved. What is the local structure of materials at something where like you can get at it with TEM? And I think that's very, very exciting to do. So I fully agree that, that's a really, would be very beneficial, and but we've yet to get around to it. The addition of carbon materials like carbon nanotubes and all of the rest to concrete, it depends on what function you want them to serve. So people have found that they've increased macroscopic properties in a favorable way. Carbon is also conductive, so people have looked at using it as a way of heating up concrete. Say if you're in a region that freezes all the time, can you actually heat up the concrete to thaw out ice? So I think nanotechnology combined with concrete can be very useful. What people find is the question is how much does it cost? So I would say that if you have a low cost way of making carbon-based materials, especially those that have high surface areas, they can be very beneficial to certain properties of the concrete.
Okay, well, thank you, and really congratulations again for your great work. Thank you.
Thanks.
Looks like we've got a couple more questions in the chat, or a couple other people have their hands up. If you'd like to ask a question, go ahead and raise your hand. Oh. Jake, would you like to ask your question?
Sure. First, I wanted to say thank you for the talk. I found it very interesting. And it's funny, actually, that cost just got brought up, because that had to do with the question that I was thinking this whole time. Is it's probably going to be very difficult to sell to companies an alternative to concrete, just because of what it is and what it's used for. And I was wondering how the materials that you're using, if that has a large cost effect on how much it would take to implement it on the mass on a mass scale in general.
Yeah, I mean, that's a very relevant question, both in terms of cost, but also availability of raw materials. The amount of concrete we use is vast. We use so much concrete, it's second only in terms of volume that we use to water. So water is the most consumed material on Earth by society. Concrete is second. So you really need to look at using materials that are abundant on the Earth's crust around the world. And limestone is one of them, and clays are also one of them. So with a lot of the research we're doing now, the availability of the metallurgical slags and the fly ash is not huge. Fly ash, hopefully the amount will go down over time because coal power hopefully is going to be reduced in terms of its usage, and the metallurgical slags are just not produced in high enough quantity that we could there would be excess to be able to use for the alternative cements. That leaves calcine clays. So there are a lot of clays on the Earth's crust. So the hope is with the alternatives, using something like the calcine clays would be a viable approach. Now, let's get back to cost. If you try and make, say, alkali-activated concrete using the current cost of the starting ingredients, especially the activator, it's hard to be cost competitive. One of the reasons is the activators are very high quality for the moment because they're produced for industries like the food industry or the paper industry. And so because of this high quality means that high cost. As with any kind of new technology, the hope is that over time, once supply chains get set up, those kind of things, the cost will decrease. The other, on the flip side as well, is with carbon incentives, as those come into play, that will also make it more attractive to use alternative types of concrete. And for example, in New Jersey at the moment, they're trying to pass a bill whereby there are incentives if the government projects are to be using sustainable types of concrete. The last thing I'll leave with that question is a comparison to another technology that started out a lot more expensive and over time has significantly decreased. And that's photovoltaics, solar cells. A decade ago, they were a lot more expensive compared to what they are now. Now they're cost competitive with other forms of how we produce electricity. A decade ago, that was not the case. And so that shows as an industry grows, as a material is used more extensively, the economics get better.
Very interesting. Thank you. I appreciate it.
You're welcome.
Thank you so much, Claire. Let's thank Claire one more time.